Okay, why don't we get started? I have a joke, but I'll do it during lecture. For those who want to look in the future at partial eclipses of the sun, or look at the uneclipsed sun, looking for, say, sunspots, or monitoring the position of the setting sun, like you can look at it like this, then take the glass away and see roughly where it is on the horizon. These pieces of glass are useful for that, and I went to one supply company today and they were sold out, and another welding supply company had about 200 of them, so I bought them all. And they said, is an eclipse coming? And I said, no, but people can get these things before an eclipse is coming. And partial ones you're likely to see at some point, so you might as well have one of these pieces of glass if you wish. So there it is, and I've got a bunch of them, $2 either today or tomorrow, or I'll bring them next week. No particular hurry, but I've got a bunch of them here today. Okay? There was a couple of questions last week, actually, on why the path of totality, that is the moon's shadow on the Earth, has different widths on the Earth's surface. So I thought I'd talk about that for a minute before class actually starts formally. For a moment, ignore the regions near the North and South poles and just take the paths that cross the Earth somewhere near the equator. You'll see that some are pretty fat, like this one, 2009, July 23rd. It's several hundred miles wide. And others are really quite skinny. Here's one, especially near the end of it, which is really pretty skinny, 2020, December 14th, and here's some skinnier ones and stuff. So the reason that the paths have different widths is that the moon's distance from the Earth varies by quite a lot because it has an elliptical orbit around the Earth. In fact, sometimes, as I said, the moon is so far away that it looks too small to cover the sun's surface or photosphere. In that case, you get an annular eclipse. But if it's not quite that far away, let's say it's a bit closer, but it looks only barely big enough to cover the sun's surface, then the amount of time over which that perfect alignment occurs is very small. And that tends to make a very narrow shadow, because if you're not quite collinear with the moon and the sun, that is, you're a little bit away from the path of totality, the moon doesn't quite cover the sun, all right? And if you're a little bit on the other side, it doesn't quite cover it as well. If the moon is just barely covering the sun, your degree of collinearity has to be very precise, and that means if you're off of it a little bit, you won't have a total eclipse of the sun, and so that tends to make a very narrow shadow path. However, suppose the moon is pretty close to you in its elliptical orbit. Suppose the moon looks big, like at perigee. You don't have to memorize that terminology, but perigee is when it's close to you, and apogee is when it's farther away. When it's at perigee, it looks easily bigger than the sun, and so, yes, if you're precisely collinear, you will see a total solar eclipse. But if you're a little bit off from precise collinearity, the moon still is big enough to cover the sun, right? So there's a relatively wide path for the eclipse during those stages, and that also tends to make a relatively long eclipse because it takes a while for the moon to completely go across the sun and start uncovering it again. So you get wide paths when you have the moon relatively close to us and narrow paths when the moon is relatively far away. Similarly, you get longish eclipses up to 7 minutes when the moon is close in, and short eclipses when it's farther out. Okay, that explains the differences near the equator. But then you might say, why, are the paths so wide near the poles? Why should the moon look bigger from the poles, etc., etc., etc.? Well, it doesn't. Can anyone venture a guess as to why the paths near the poles are so much wider than the paths near the equator? The Mercator projection. Several people said Mercator. Was that Michael there? You said Mercator projection, and someone else said Mercator projection. Yeah, the Mercator projection tends to expand areas, the apparent size of areas near the poles, because of course what's really happening is that near the poles the land is coming together toward the pole, but the Mercator projection spreads all that out into parallel lines of longitude, whereas actually the lines cross near the poles. And so land areas near the poles look enormous. I mean, Greenland is a pretty big place, but it is not the size or bigger than the size of all of North America. And the Antarctic, look at the size of this thing. First of all, its shape is totally wrong, right? Second of all, according to the Mercator projection, the area of the Antarctic is similar to the combined area of everything else, it seems, near the equator, and that's simply not true. So the Mercator projection expands the apparent area on a spherical surface when you flatten it onto a sheet of paper. The other effect that you get is related to the Mercator projection, but is not exactly the same, but it contributes to this effect as well. If I have a beam of light shining at the equator face on like that, it looks, relatively narrow. I should use my laser pointer, but I forgot to take it out. And oh yeah, there's one right here, actually. That'll look better. It's also brighter, I think, but it might not illustrate the effect quite as well because the beam is so narrow. It's kind of a weak beam. Let me do this. So when you're shining on the equator, the beam looks pretty narrow, although it's kind of wide because this flashlight is wide. But look what happens when I aim near the poles. That tubular beam of light is now intersecting a large area of the Earth because the Earth itself is slanted. It's sort of like if I hold up a sheet of paper perpendicular to the beam of the path, the beam of light, it takes up some area. But if I now slant the paper, the amount of area that's hit by the beam is larger, okay, because it's coming in at a glancing angle. So a given perpendicular width of the beam actually spreads out over a larger area. We'll come across that concept again in a few minutes when we discuss the seasons. It's also part of the reason why it starts getting cold in the late afternoon, early evening, when the sun is getting low, because the beam of light is now being spread out over a larger area of the Earth's surface, and so per unit area, you're getting less heating. But anyway, it's this effect that also tends to artificially inflate the amount of area that's being covered. But this is a real effect. There is a lot of area being covered by the eclipses down near the south and north, whereas the Mercator projection is just a fake thing. It's an apparent effect, not a real effect. It's an apparent effect of taking a spherical surface and flattening it out onto a flat sheet of paper. So there's these two effects that make the paths wide near the poles. One is a very real effect of the paths being wide, and the other is just an apparent effect, and that tends to make the paths super wide. So I just thought I'd mention that because a couple of people asked about that after class. Okay, any questions? All right. So quiz and discussion section, maybe many of you have already had it. Homework 3 due on Friday. Final star party of the week for our class is tonight. We'll see how the weather turns out, 8 to 9 p.m. And then I still have some extra office hours this week. In addition to the ones after class, I'll hold one before class on Friday. Okay, let me just review a little bit of where we left off on Monday. I mentioned how the sky is subdivided into these fairly arbitrary constellations. There are 88 of them. Some come from modern times, like in the southern hemisphere, there's one called Telescopium, and clearly that doesn't come from the ancient Greeks, okay, or the ancient Egyptians or Chinese, so that's a more modern constellation. But anyway, they're pretty arbitrary, and each star is in one and only one constellation. So there are discrete boundaries among the constellations, and each star is in only one constellation, but basically astronomers don't even really care what constellation they're in, because constellations have no real physical meaning. Nevertheless, they're kind of fun. They're fun to learn. You can earn your Eagle Scout badge in astronomy by learning constellations, but you're not going to pass the tests in this class by learning constellations because they're not very physically meaningful. But there's mythology associated with them, and you can have T-shirts that have them. Northern constellations are on the side that faces you. Southern constellations are on the other side. So we don't usually see very many of the southern constellations, but I thought I'd wear this T-shirt today. Okay, and then getting to somewhat more fundamental things, I started talking about the celestial sphere and how the stars appear to be plastered to this big dome that surrounds us, and the dome appears to rotate. Of course, we now know that that apparent rotation of the celestial sphere is simply a reflection of Earth's intrinsic rotation about its axis. So you could be standing on the Earth here, say on the equator. Let's put you in Bogota, Colombia, and you're a very large human compared to the Earth. And, you know, as the Earth rotates, you are seeing different directions in space, and so the stars rise and set, as does the sun. But it's entirely a reflection of Earth's rotation. Now, it's important to understand what we mean by the horizon and the zenith at a particular point. So the zenith is simply the point that's straight overhead. Okay, so here's the zenith of A, of someone at position A. They see the part of the celestial sphere that's over here. And by the way, this sphere should be drawn very, very big compared to the size of the Earth. Much bigger than what I've shown here on a relatively small and finite, PowerPoint slide. But it should be extremely large compared to the Earth. You can think of it as being infinitely far away, although, as we will see later, the stars aren't infinitely far away, and there are even ways we can tell how far away different stars are. But anyway, the overhead point on the celestial sphere for person A is over there. For person B, it's over here. So these two people would see different stars overhead, far, far away. The horizon of a person is simply the tangent to the Earth at the position of the person. And that's because if you look over in this direction, what's happening? You're looking through the Earth, right? So you wouldn't see the stars if you were looking in that direction or down into here. You can only see things that are, broadly speaking, to the left of this nearly vertical line as I've drawn it here. You can see things over there, or there, or there, or there, or there. I should attach a mouse because my finger is a little bit sweaty and it's not doing well on this touchpad. But anyway, you can see things that are not blocked by the Earth. And in the approximation that the celestial sphere is huge compared to the radius of the Earth, you can see that at any time, given a clear horizon, a given observer can see half of the celestial sphere. You go out to here, you can see everything along this arc here, all the way down to there, because the horizon extends out to the celestial sphere out to there. So that's about half of the celestial sphere. And in the limit that the sphere is much, much bigger than the radius of the Earth, this becomes exactly half of the celestial sphere. But notice observer B sees a different half of the celestial sphere than observer A does. At this moment, observer B basically sees these parts of the sphere. Are there any parts of the celestial sphere that both observers A and B can see at this time? Yes, which parts? Yeah, up at the top, a lot of people are saying. Up here in this conical region right there, these stars are above the horizon for both observer B and observer A. Are there any stars that neither A nor B can see at this time? That's right, the ones that are down in this conical region over here. They're all below the horizon of both A and B. So you should think about that and understand that. Now, the poles of the Earth, the poles around which, or the axis around which Earth rotates, can be extended out until they intersect the celestial sphere. And those are two special points. They're called the North Celestial Pole and the South Celestial Pole. Similarly, if you put a light bulb in the middle of the Earth, and suppose Earth were transparent except for a dark line along its equator, that line would cast a shadow onto the celestial sphere. That shadow is called the celestial equator. So it's just an extension of Earth's equator along the same plane out to where it intersects the celestial sphere. Okay? And as the Earth rotates, the celestial sphere rotates, and so stars appear to go around in circles around either the North Celestial Pole, if that's the one that you see above your horizon, or the South Celestial Pole, if you happen to be in the Southern Hemisphere. I'll show examples of that in a minute. Where would you have to be, do you think, in order to see the North Celestial Pole at your zenith, or on the zenith? At the North Pole, that's right. If you were standing right here, the North Celestial Pole would be in the same direction as your zenith. And what would be along your horizon? The celestial equator, exactly right. The celestial equator would be on your horizon. If you're at the equator, what would be straight above you? Part of the celestial equator. What would be at your horizon? The celestial poles, both of them, yeah. And then if you were somewhere in between the North Celestial Pole and the equator, you would see the North Celestial Pole at some elevation, some altitude above your horizon, and you would see the celestial equator at some altitude above your horizon as well. And one can figure those things out if one wants to. Okay, so let's show some little animations here. This is done by a colleague of mine who happens to be at Ohio State University in Columbus, Ohio. So there's Polaris. We happen to have a star very near the North Celestial Pole. It's not exactly at the North Celestial Pole, but it's roughly there. So let's see what happens during the course of a night. You see the stars going around in these circles around the North Celestial Pole. And I encourage you someday to go out in a sleeping bag and just watch the sky for a long time, and you will see, after a while, this slow drift. If you photograph it, you can see the lengths of or you can see the actual arcs of the stars as they go across the sky. And you take such a photograph by taking usually a single reflex camera or some other camera that allows you to take a long exposure. Instamatic cameras generally don't allow that. And even modern digital cameras, the cheap ones, typically only let you expose for, 10 or 15 or 20 seconds, not, half an hour or 3 hours or whatever. But one of these cameras, I don't even think this one works anymore, but it has a setting called B for bulb, and you usually use a cable release, open the shutter, leave it open for as long as you want, and then close the shutter. And usually you attach this to a tripod, point it at some region, some direction in space, and as the Earth rotates, that direction in space corresponds to different stars in the sky. Or saying the same thing, the stars appear to drift across your photographic field of view, and then you stop your exposure like this. But don't try this with an Instamatic because it simply won't work. You need something that allows you to do a long exposure. And by the way, turn off the flash. The flash does not help to illuminate stars tens of light years away. Okay? It would take years for the flash to get there, and by the time it got back to you, it would be so weak that the effect would be negligible. There's, by the way, a shooting star, a meteor. It's not a star at all. We'll talk about that later. Near the southern hemisphere, you can also do this as well, or in the southern hemisphere. The South Celestial Pole doesn't happen to have a bright star near it. I mean, there's nothing special about Polaris except for its location. Some people think that it's the brightest star in the sky. No way. It's just a mediocre brightness star. It's visible to the naked eye, but it's not particularly brilliant or anything. It just happens to be in the right place. It's not special in any other way. The South Celestial Pole doesn't happen to have a reasonably bright star near it. That little thing there is pretty faint. By the way, can anyone tell me about how long this exposure was? Long, yeah, not short. About how long do you think? Yeah, almost 12 hours, because maybe 11 hours. These arcs, it's even hard to follow them to see where they end, but they go almost one halfway around the full circle. And what is the full circle? 24 hours, because how long does it take for us to go through one rotation? 24 hours. There you go. Okay. Suppose we're standing on the north pole of the Earth. What would the stars do as viewed by us? So now my little guy is standing right here at the pole. So he's just sort of turning around like this. Do stars ever rise or set as viewed from the North Pole or the South Pole? No, I see a lot of people shaking their heads. No, they don't, because you're just turning with the Earth right smack coincident with the axis of rotation. So the stars look like they undergo circles that are parallel to the horizon, but your horizon never changes. So the Polaris is up there somewhere, and the circles are smaller the closer you get to Polaris, and bigger the closer you get to the horizon. But they never rise or set. So here's an example of that. Viewing from the North Pole, The stars never rise or set. It actually looks like they're curving down a little bit and then curving up, but that's a distortion associated with the fact that we're projecting a spherical surface on a flat plane. It's related to this Mercator projection problem. The surface of a sphere is a different kind of geometry than that of Euclid, than that of a flat sheet of paper. And that'll be important when we discuss the whole potential shape of the universe later on when we do cosmology. Okay, what if we're standing on the Earth's equator? By the way, stars that are always above your horizon from any given location are called circumpolar stars because they're always above the horizon. So these stars are circumpolar. Is that one there circumpolar? No, because it goes below your horizon. Okay, or that one there certainly goes below your horizon. So from an intermediate latitude, some of the stars are circumpolar, some are not. From the North Pole or the South Pole of the Earth, are all the stars circumpolar, none of them, or something in between? What do you think? All the stars are circumpolar because all of them are always, all of the ones you see, I should say, are circumpolar because they never go below the horizon. You don't see half of the celestial sphere. You don't see the half that's in the southern hemisphere. But the part you see is entirely circumpolar. None of these stars is rising or setting. They're all just cruising parallel to the horizon. Okay, now, conversely, suppose you're looking from the Earth's equator. Now, let's put our guy this time, I don't know, let's put him in Cambodia, right there. All right, that's not what I think of Cambodia. It's an interesting place, but I just stuck my guy there. All right, so as this guy is rotating around, he or she sees stars rising and setting perpendicular to the horizon, right? They're coming straight up out of the horizon, going across the sky and setting straight down. Let's show that here. Here they are, rising straight up out of the horizon, going across the sky and setting straight down. For an observer at the Earth's equator, are any of the stars circumpolar? No. You could say the North Celestial Pole is right on the horizon, and so that's sort of a singular point. That's just one point. Essentially none of the sky is circumpolar, basically. If I were to ask this on an exam, the answer would be none of the stars are circumpolar, and I wouldn't want you to argue that the one right at the pole is right at the horizon because, that's a silly little technicality. But anyway, I don't want to trip you up on technicalities of this sort. Now go to some intermediate latitude, and what you see is that the stars rise at an angle relative to the horizon, swoop across the sky, and then set in the west. So they rise in the east at an angle that's not vertical, and they set in the west. And here are the star trails that you would get if you were to photograph these things over many hours in this particular case. All right? So stick your guy on different parts of the Earth. You can buy these little Earths or just take a ball of styrofoam or something and play around with someone standing on different parts of the Earth and imagine to yourself what he or she would see, because this kind of geometry is not something we normally think about. We don't normally think about spheres and stuff. We think about geometry on a sheet of paper, and that's a different kind of geometry. And it can take some thinking to convince yourself that you understand what someone at various intermediate latitudes would see. Okay? And there's a homework question today or this week that helps you play with these concepts. Any questions on that? Okay. Our view of the night sky changes not only over the course of a single night, but also over the course of the seasons. The seasons being basically just a reflection of where we are in our position around the sun. Let me show you here what I mean. In December, let's suppose the Earth is here relative to the sun, and over the course of a year, the Earth goes around the sun. That's 1 year. 1 day, of course, is the Earth's rotation. It's amazing. Occasionally, Newsweek and Time Magazine do these surveys of the general public, and they ask them what a year is, and people say it's the period over which the sun goes around the Earth, physically, and oh my God, and yeah, hopefully not here at Cal, but anyway, and then other people, they might get the year right, that it's 365 days, but But they still say that the sun orbits the earth and other stuff. So, and then, you ask them what a day is, and they get all confused. But okay, so here we are in December, and here's the night side of the earth, and here's the bright side of the earth. Again, the night side should look darker, but in order to be able to see it, the publisher made it look a little bit light. But anyway, if you're standing somewhere near the equator, and I'm putting ourselves near the equator somewhere because near the poles you get extra weird technical effects. Near the equator or within 10, 20, 30, 40, even 50 degrees of the equator. Here in San Francisco, Berkeley, we're at about 38 north latitude. All that I'm saying basically works, but if you're near the poles, you can get to some odd viewing effects. But anyway, if you're somewhere near the equator, overhead at night in December is the constellation Orion. Okay? Now, in June, the direction of Orion happens to coincide with the direction of the sun. So you don't see Orion at night. In fact, you don't see it at all. You could see it during an eclipse of the sun, I suppose. Instead, the overhead point is off towards some other constellation, Ophiuchus. Okay, I've forgotten who Ophiuchus was. But Orion is the great hunter. Doesn't really matter. Okay. In March, you're seeing Virgo here, supposedly a virgin. Okay. And that's at midnight. But what time of the day corresponds to this arrow right here? What is this arrow experiencing right now if the Earth is rotating like this? Sunset. There you go. A bunch of people said sunset. So at sunset in March, the direction to Orion, and remember, Orion's very far away. The stars are very far away, and that's why I've drawn all these arrows parallel. I didn't draw this arrow pointing to Orion right here, because Orion isn't just above the Earth. Orion is very far away. Okay, remember, when you're looking at things very far away, the light rays are coming in parallel. So this is the direction of Orion overhead at sunset. Well, gee whiz, sunset is 6 hours earlier than midnight, right? So you're seeing Orion 3 months later than December. You're seeing it in March overhead 6 hours earlier than you see it overhead in December, right? And probably this was not a discontinuous jump, like February 22nd, Orion didn't suddenly decide to move over from one part of the sky to another, right? Probably this was the cumulative effect of a bunch of little steps each day. Indeed, that's the case. Over here and here and here and here, you would see Orion overhead at slightly different times of the night, earlier and earlier than midnight as you go progressively farther in Earth's orbit. Indeed, it turns out that you would see Orion at a given position in the sky at a time on your clock that's 4 minutes per day earlier. And indeed, 4 minutes per day times 90 days by advanced mathematics is 360 minutes. And a simple conversion tells you that that's 6 hours. So indeed, the apparent position of Orion is the same, but at times that differ depending on where Earth is in its orbit. And basically, as a good rule of thumb, a given star will cross the overhead point or the highest point in the sky, or it'll rise or set or whatever. Take any meaningful time for a star, rising, setting, crossing the highest point in the sky, whatever. That position in the sky will occur 4 minutes earlier per day. And cumulatively, after many, many days, you notice that a given constellation rises several hours earlier, and finally 6 hours earlier, and finally 12 hours earlier. In fact, at this time, you don't even see Orion. So you get this cumulative 4 minutes per day business, and that means that at different times of the year, you are seeing different constellations. But the same constellations at some of the times of the year can be seen at different times of the night. You can see Orion at sunset in March. You can see it overhead at midnight in December. You see Orion at what time do you think in September? At sunrise. That's right. A couple people said sunrise. You see it overhead. And when would you see, quote unquote, Orion in June overhead? Noon. So you wouldn't see it. There you go. Okay, so the changing seasons also gives rise to a changing set of constellations that's up in the night sky, although the specific constellations that are up also depend on what time of night it is. Okay, so there are two effects here. Okay, is that pretty clear? Think about it. This can be a little bit confusing. All right, then finally, I want to talk a little bit about the seasons and then move on to other things. There's enormous confusion among the general public on the cause of the seasons. And again, these polls by Time and Newsweek show this all the time. Most people think that the seasons are due to Earth's changing distance from the sun. They've heard that Earth's orbit is not quite circular, it's elliptical, and they say, well, Earth is warm during the summer and cold during the winter, so that must mean that it's an effect of distance from the sun. Okay, that's not what it is. You may think that. That's okay. Let me teach you what the correct explanation is. If, I can ask you, first of all, if the effect of the seasons were due to a changing distance from the sun, primarily due to a changing distance from the sun, what aspect of the seasons could you not explain? Yep, go ahead. Different seasons in different hemispheres of the Earth. Right, what's your name? Katrina. Okay, Katrina says different seasons in different hemispheres. They're opposite in the southern hemisphere. Very true. But suppose I were a skeptic and I said, how do I know that the seasons in New Zealand and Australia and South America really are the opposite from here? Maybe that's just an urban legend. How do I know? What easily observable thing could I notice standing here in Berkeley by looking at the sky day after day that would tell me something about the seasons not being due to a changing distance? Brett. The days and nights change length. Very good. What was another person going to say over here? Same thing? Yes? Someone had their hand up right here. No? Okay. If you were going to say, well, it's warmer in the summer and colder in the winter, I would say, no, that's not always true. There are cold days in the summer. Depends on weather patterns, and there are hot days in the winter. So it's not always true that the temperature of the day is exactly correlated with the season. But the length of day and night is absolutely correlated with the time of the year. You will never have a winter day in the northern hemisphere when the sun is up for only a short time. It will never happen. It might be cloudy, you might not see the sun, but it's still up. So the length of the day and night is something that is absolutely correlated with the seasons, and that clearly has no relation to Earth's distance from the sun, because the length of the day and night is determined only by Earth's rotation period, and it's independent of the distance from the sun, right? Okay, so what are the seasons caused by? I shouldn't have had this slide up all this time. But, it's probably not a surprise to people, so I don't like, to do this little striptease and stuff. The seasons are due to the fact that Earth's axis of rotation is not exactly perpendicular to its orbital plane around the sun. Rather, it's tilted by about 23.5 degrees. And that tilt over short time scales, the time scale of our human lives and stuff, is constant. So as I move the Earth over to here, I have to maintain the same tilt, that is the same orientation relative to some absolute space. Not necessarily relative to the sun, but relative to the stars up into the sky. So here we are, let's say in summer, where the northern hemisphere is basically tilted to the sun. It's not that the northern hemisphere is significantly closer to the sun. I mean, it is by a tiny bit than the southern hemisphere, but that's not the main effect. The main effect is that by being tilted toward the sun, as the Earth rotates, the sun is above the horizon for one heck of a long time. And moreover, the sun is higher in the sky than is seen from the southern hemisphere, so its rays come straight down on us and heat every unit area of the Earth more than they do when the sun is at a glancing angle. I'll show a slide of that in a minute. All right? So here you have long days and generally warm days, but not always. What was that Mark Twain saying, that the coldest winter day I ever spent was a summer day in San Francisco, because it's always foggy and stuff. Anyway, with the seasons, 3 months, okay, so here you have when the northern hemisphere is basically pointing toward the sun, you have long days and short nights in the northern hemisphere and short days and long nights in the southern hemisphere. 3 months later, what's going on? What's pointing sort of more or less exactly toward the sun? Earth's equator, that's right. So the northern and southern hemispheres have pretty much equal treatment at the equinoxes. Okay, but then you move into northern hemisphere fall and finally winter, and which hemisphere gets the preferential treatment in terms of amount of sunlight, both in terms of how direct it is and how long the sun is up? The southern hemisphere, that's right. Okay, and then 3 months later, it's an equinox again. We're almost at one. In a couple of days, the autumnal equinox. Where is the Earth at the autumnal equinox? All right, tell me when to stop. Right there, stop. Right, there we go. Okay. Now, the days are always 12 hours long, 12 hours of darkness and 12 hours of daylight near the equator. Okay, even though they're longer in the northern hemisphere and shorter in the southern hemisphere, it's still 12 and 12 at the equator, and it's 12 and 12 throughout the year on the equator. But it varies from being more than 12 hours of brightness in the summer in the northern hemisphere to being less than 12 hours of brightness in the winter, in the fall and the winter in the northern hemisphere, and conversely for the southern hemisphere. So it's entirely a function of the tilt, and here in these diagrams I think you'll be able to reconstruct much of what I just said. Okay? Now, it's a historical accident in a sense that the first day of summer is defined to be the day when Earth's northern hemisphere is most pointed toward the sun. I would say that's midsummer. Right? Astronomically, it's midsummer. But people call it the first day of summer, and then the following 3 months are summer. Even though, gosh, it looks like it's, should be fall, part of the time. But it's defined that way in part because the temperature of the seasons does have a certain lag. The hottest days in Berkeley tend not to be in June. They tend to be in July and August. And elsewhere, that happens to be the case as well. So that's because it takes a while for the oceans to warm up and all that, and the cloud cover and other things depend on the temperature of the oceans and the atmosphere and all this stuff that takes a while to heat up. And so you tend to get the hottest temperatures late in the summer. But astronomically, this is the first day of summer. That's the first day of fall. That's the first day of northern hemisphere winter. And this is the first day of northern hemisphere spring. Okay? So think about that. So I have all these little things here. I have these diagrams, but I thought I'd show you some pictures from the South Pole. Oops, that picture got flipped. This is one of our former graduate students, Jamie Lloyd, who's now a professor at Cornell, and he did some observations near the South Pole, and somehow my slide got slipped, but it says here, geographic South Pole, and he looks pretty cold there, and he's holding an Australian flag because that's where he's from. But anyway, that's not to imply that Australia is part of Antarctic. Anyway, it's cold because the sun is low on the horizon, and in the winter it's actually below the horizon for about 6 months, and in the summer it's above the horizon for about 6 months, but it's always pretty low above the horizon. You think about it like this. Here's the tilt. Oops. And from the South Pole, you are seeing the sun above the horizon, but it's not much above the horizon the way it is, say, near the equator or near the tropics, okay? And here's the sun setting, and how long will it be down? About 6 months, that's right. And play with the diagrams and these little gizmos here. You can see that as soon as the Earth gets to this position, the North Pole, let's go over to here. The North Pole starts seeing the sun, the South Pole doesn't see the sun, and for 6 months thereafter, the North Pole sees the sun and the South Pole does not. Then starting from this position here, the South Pole starts seeing the sun and the North Pole does not because it's blocked by the Earth, and that lasts for 6 months. So the days and nights are 6 months long right at the poles, and it gets really cold at night, and even during the day it doesn't get all that cold, all that warm, because the sun is never very high above the horizon. And this effect comes into play that I mentioned a few minutes earlier, where when the sun is high above the horizon, a given beam of light, let's take my flashlight beam again, hits a relatively small area. But when the sun is only low above the horizon, as it would be as seen by someone near the poles here, because see, their horizon is this thing here, and my flashlight's coming from over there, whereas for the equatorial guy, their horizon is these directions, and I'm overhead, so the dot is bigger. But near the poles, the dot is spread out because of this angle here that the Earth's surface is making relative to the beam of light. And that beam of light then illuminates a bigger area on the surface of the Earth. So the amount of heating per unit area is smaller. Okay? So you don't get all that warm even in the summer at the poles, although it's not that bad. It's not, incredibly cold. It's just pretty cold, but it's not as cold as it is at night, okay? So in a sense, I say that the sunlight is less direct. I mean, it's direct, but the point is it's covering more area. The same amount of energy is being spread out over a bigger area. All right? So that's the cause of the seasons. The sun's path in the sky can be represented this way. In the northern hemisphere, spring and fall, the sun goes arcing high above the horizon and spends a long time above the horizon and only a short time below the horizon, so the nights are short, okay? On the equinoxes, the sun is basically following the celestial equator, okay, like this. Not quite the celestial equator, it turns out, but it's near the celestial equator. The celestial equator and the sun's path are not exactly the same thing, it turns out, because of this 23.5 degree tilt. But in any case, the sun is somewhere near the equator. And then in December, you can see that from the northern hemisphere's perspective, the sun is above the sky, above the horizon in the sky for a relatively short fraction of its total 24-hour arc, and below the horizon for a long time. And there's a cool little applet, and all the applets, I think, are now on the web, but here as seen from somewhere, Texas, I guess, where does it say? It doesn't say. I think this is somewhere from Texas. It doesn't really matter. There's a sunrise at different times of the year. So in January, you see sunrise is sort of in the south. Now at the equinoxes, it's due east. And then as you go into the summer months, it rises north of east. And then in the winter months, it rises south of east. And at the equinoxes, it rises due east. So, and you could play this game. Yeah, Big Bend National Park, Texas. Okay, who cares? But in any case, this shows that in the summer, the sun rises north of east, somewhat north of east, and in the winters, the sun rises somewhat south of east. And similarly, it sets somewhat north of west and somewhat south of west as well. So that's kind of cool there. Here's a photograph, I think, taken from Greece, showing the sunrise at the summer solstice, June 22nd, and this is north of east. At the equinox, it's due east. And at the winter solstice, December 22nd, it rises south of east. And that's essentially what we're showing here, but in a three-dimensional way. So that's what the seasons are caused by. Now, the seasons are indeed opposite in the southern hemisphere, so I'm not, you can believe that they are. But there are a few other things that are opposite, and then I'll answer a question. There's a couple of questions, but let me tell you a little joke here first. Other things that are opposite are the direction in which stars appear to go around the poles. In the northern hemisphere, the stars rise in the east and set in the west, okay? Well, these are circumpolar, but if you took a star here, it rises in the east, goes across like that, sets in the west. So it's going counterclockwise around the pole. In the southern hemisphere, the stars rise in the east and set in the west, and it looks like they're going clockwise around the pole, because this is direction east in the southern hemisphere, and that's the direction west. If you were facing the south pole, that's what you would see. So they go clockwise around the pole from the southern hemisphere and counterclockwise in the northern hemisphere. Other things that are opposite is the constellations look sort of upside down. Here's Orion as seen from the northern hemisphere, the head of the hunter, the two shoulders, the belt, the sword, the 2 feet. So Orion is standing straight up as seen from the northern hemisphere. But from the southern hemisphere, he's upside down like this. So he's sort of standing on his head, and he's flipped left and right as well. So that's something that's opposite. The crescent moon points in the opposite direction, it turns out, though I don't have any photographs of that. So there are some things that are opposite. But unbeknownst to me, it turns out that airlines also have different rules regarding their utensils in the southern hemisphere compared to the northern hemisphere. You know, when you fly around in the US, especially after 9/11, they give you a plastic spoon, a metal spoon sometimes, and a plastic fork and a plastic knife, because knives and forks make better weapons or potential weapons than do spoons, right? So how many of you have been on flights where you got a metal spoon and a plastic knife and a plastic fork, right? Well, I'm sure many more of you have, but you just didn't bother to notice. But that's what most airlines in the US and Europe do. But flying down to Tahiti 2 years ago, I was astonished to find that on Air Tahiti Nui, they gave us a plastic spoon and a metal fork and a metal knife. Like, on guard, you know, a spoon is a deadly weapon, and they're not really very worried about knives and forks. Now, I'm only kidding in that I don't think this is a generic feature of flights down to the southern hemisphere. I've flown down to Australia and New Zealand, and it doesn't seem to be that way. I don't know why Air Tahiti Nui does it that way, okay? But I thought it was kind of funny anyway. All right, you'll bear with my sophomoric jokes, but anyway, okay, question in the back there about the seasons. I'm sorry, what? Oh, turn off the flashlight. Thank you. Okay, cool. Kudos to you. What's your name? Pardon? Patrick. All right, you're kind of far back, but I'll try to recognize you on Friday. Patrick says, turn off your flashlight. Was it shining in your eye, or were you just trying to save me battery power? Oh, cool, okay. All right, a question about the seasons? But no, thank you, Patrick, thank you. All right, let's move on then to other things. I want to spend just a couple of lectures on studies of, or sort of early studies of the solar system. You know, people on Earth who study the solar system and how they went about doing it and what they learned, because it's historically important. And although studies of the solar system were done from many places on Earth, among many cultures, Greeks, Chinese, others, you know, in Egypt, much of what we have been handed down stems from the ancient Greeks. And since I only have a couple of lectures in which to do this, I will focus on first the contributions of the ancient Greeks and then the contributions from Western Europe. But that's not to imply that the rest of the world was stuck in some dark ages. Indeed, in many cultures, they were more advanced than the Greeks were or the Europeans were. But I only have 2 lectures, and so I'll talk about what sort of has influenced us here most in the Western Hemisphere. Okay, well, you notice that the stars in the sky undergo a daily east to west motion, which we now understand to be due to essentially a reflection of Earth's rotation about its axis. That's called the diurnal motion. It's just the daily east to west rising and setting of the stars, the sun, and so on. And all the stars pretty much do this, and they maintain their same patterns from night to night. Orion always looks about the same, at least over a human lifetime. But people notice that some points of light in the sky appeared not to maintain a fixed pattern relative to other stars. They seemed to move around. They were called the wanderers, planets. Planet comes from the Greek word for wanderer. And let me show you some examples. Here's a series of photographs I took a few years ago. This is Venus. This is Mercury down here, rarely seen. This is Mars, and that's Saturn. And all the other things are stars. That's Aldebaran, and here's other stars. Jupiter's off to the upper left here, but I wanted to focus in on just these 4 planets here. A day later, I think, 2 days later. Oops, why is it not going? There it goes. Notice in particular this little triangle here. Let me go back. It almost looked like a little isosceles triangle here with Mars, Saturn, and Venus. Oops. Look at it now. It's almost like a right triangle almost. And Venus is closer to Mars, and Saturn is a bit farther down. And oops, sorry, I'm goofing up here. A couple of days later, Venus is now very close to Mars, and the separation with Saturn is beginning to get pretty big. Aldebaran's way down here now, and Mercury has risen higher up relative to Aldebaran, so to speak. And later still, there's Venus. It's passed up Mars, and Aldebaran has now set. It's way down in the muck somewhere. There's Mount Tam. So these things, these points of lights, the planets are moving relative to the stars from west to east, because this west is this direction and east is generally across the sky, arcing over my back to the opposite direction. And a day or two later, even the crescent moon came up. And look at that. What's that showing there? Earthshine. Yay, all right. And now Venus has totally passed up Mars. And so Venus is cruising along. Mars is cruising too, but not quite as fast. But it's clearly cruising relative to Saturn, which is being left behind in the dust. And Mercury is now way down there. But anyway, the planets move relative to the so-called fixed stars. And the ancient Greeks and others noticed this and called them planets, the wanderers. And they very naturally thought that the planets are these entities that they attributed to gods or named after gods, or even thought that they were the gods themselves in some cases, and that they rotate around the Earth, which was thought to be the center of the universe, on different spheres than the sphere that contains the fixed stars, the firmament. And this idea was developed by Aristotle around 350 BC or so. And the basic idea survived for nearly 2 millennia. This idea that the earth and water are in the middle, air is here, fire is there. Those were the 4 elements: earth, air, fire, and water. And then there was the sphere of the moon, the sphere of Mercury, the sphere of Venus, the sphere of the sun, the sphere of Mars, Jupiter, Saturn, and then the firmament, the sphere that contained the fixed stars, which they didn't really know what they were. They didn't realize they were distant suns. They were just little jewels glued to the celestial sphere. And the Greeks noticed that the general motion of the planets among the stars was from west to east. That's what I just showed. But occasionally, for a while, the planets each year seem to go through what's called retrograde motion from east to west. And I'll show you this again on Friday, but here's the motion of Mars, prograde from west to east among the constellations. And then for a few months each year, Mars goes the wrong way in the sky from east to west. And this posed a problem, at least for the simplest geocentric models, although the Aristotelian model could be modified in a very complicated way to account for this. Aristotle had these spheres rotating in very complex ways to explain the retrograde motion. We will see, however, on Friday that there's a much more natural explanation with an Earth, with a sun-centered solar system. Okay, see you then, Brett. I'll talk to you after class. Okay. Thank you.